Okay, so this video is about some summation notation. So we're going to be summing a bunch of things together. Things like 1 plus 2 plus 3 plus 4 plus 5, maybe something like that. Or maybe 1 squared plus 2 squared plus 3 squared plus 4 squared. Maybe a couple more terms. Okay, or something like, how about 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. Something like that. Okay, on the other hand, uh, remember why we're doing these sums. These are going to be summing the areas of rectangles. Okay, and so there's going to be a pattern to the sum that we're going to take advantage of so that we can write this in compact notation. And so I'm going to rewrite these in a compact way using sigma notation. So this is capital sigma. And the way this is going to start is I'm going to use a value of an index, what we call an index k. And the k is going to range between, it's going to tell me which term I have here. So this is, the first term would be for k equals 1. And here this term would be k equals 2. And here this would be k equals 3. And so on, k equals 4, k equals 5. I don't know if that's coming into focus. I've been having trouble with the focus this morning. Let's see if I can do there. Okay. K equals 4, k equals 5, and so on. So k is index. Let me say that again. K is an index that indicates which term you're on. So we'll start with k equals 1 here to 5 because I have 5 terms. And then the pattern is that I'm just summing the value k. Okay. So that represents, again, when k is equal to 1, you have a 1 plus, the sigma is the plus here, k equals 2 next, plus k equals 3, plus k equals 4, plus k equals 5. So this is the starting index, and this is the ending, and this is the pattern. Okay, so what would the next one be if we were to write that in our sigma notation? Well, k equals 1, k equals 2, k equals 3, k equals 4, k equals 5, k equals 6. So I think you see the pattern here. So if we start with 1 to 6, right, then we would have a k squared here. Okay, and then similarly, this is for k equals 1, k equals 2, k equals 3, k equals 4, k equals 5. So I think we see where the k is going here. K equals 1 to 5, 1 over k. Good. Now, of course, the starting index doesn't have to be a 1. It could be 0. It could be -3. It could be any number. So let's go in reverse. I'm going to write a sigma, and you write out what the pattern is going to be. So how about a sigma k equals 3 to 6, 2 to the k. What would that look like? You can pause and write down what you think. Okay, you ready? So we start with k equals 3, so I would write 2 cubed plus, now k equals 4 next, so that would be 2 to the 4th, plus k equals 5 next, 2 to the 5th, plus 2 to the 6th. Good. Let's try another one. Oop, the pen is bleeding through here. How about sum k equals 2 to 7, and in this case we'll have, how about 2k plus 1? Oh, we'll just do 2k plus 1. Okay, how would that go? Well, first off, we're starting with k equals 2, so when k equals 2, you have 2 times 2 plus 1, which is 5. So we start with a 5. Plus, k equals 3 now. 6 plus 1 is 7. K equals 4. 8 plus 1 is 9. Excuse me. In fact, you can see what the pattern is going to be here, right? So again, this was k equals 2, k equals 3, k equals 4. How many more do we have here? 5, 6, 7. Right, so when I put in a 7, I get 14 plus 1 is 17. Okay, good. So these are the odd numbers from 5 to 15 summed together. Good. How about one more here? Because this is also a common thing to see. K equals 1 to 4 maybe. Minus 1 to the k power times, how is it just an x to the k? Okay, so what are we summing now? If I start with a k equals 1, right, I would just have a minus 1 times x, which is minus x. And then when k equals 2, I'd have a minus 1 squared, which is positive 1 times x squared. Plus when k equals 3, I plug in k equals 3, I get minus x cubed. Oops, minus x cubed. And then when k equals 4, that's my last term, I get plus x to the 4th. Good. So there's my sum. Good. Let's try going backwards. Okay, so continuing, I've got 2 examples coming from the activity. What number was that? Activity 4.2.2. So let's try this first one here. So I'm thinking, right, when I try to construct the sum, I need to figure out how the pattern uses the value of k. So for example, this could be like k equals 1, k equals 2, k equals 3, and so on. And so let's see, the other thing I want to look at is how I'm getting these numbers. So I'm starting with a 3, giving a 7, then 11, 15. So it looks like I'm increasing by 4 each time, and then I'm starting with a 3. So let's see, this could be just a 3, this is 3 plus 4, this is 3 plus 4 plus 4, this is 3 plus 4 plus 4 plus 4. So another way to say that is, let me rewrite it underneath. This is 3, this is 3 plus 4, this one is 3 plus 2 times 4, this one would be 3 plus 3 times 4, and so on. And what would 27 be then? Well, if I subtract 3 from 27, that would be 24, right? So I'm going to have a 3 plus, and then something times 4, right? So it looks like 6 times 4. Right, so I see the pattern now, and so I'm going to write this as a sum. K equals 1. I guess we could start at 0 if we wanted to. So let's go ahead and start with 0 and ends at 6. And then we'll have 3 plus k times 4. Good. Let's see, how about this next one? 4 plus 8 plus 16 plus 32 up to 256. What's common about these? Do you recognize the pattern here with these numbers? Excuse me. They're looking an awful lot like powers of 2. So how about if I rewrite these as powers of 2? 4 would be 2 squared. 8 would be 2 cubed. 16 would be 2 to the 4th. There, I think we see the pattern now. That'd be 2 to the 5th power. And then that ends with 256, which is going to be what? So you can take a moment to check on your calculator, but I believe 256 will be 2 to the 8th power. Okay, so we have 2, 3, 4, 5, 6, 7, 8. So this is going to be equal to the sum. K equals 2 to 8, and then we just have 2 to the k. Good. So going this way is a little bit harder, right? Because you're looking for a pattern for the k value, but here you're given the pattern, so you just have to expand out the pattern. Very good. So that's how we work with Riemann sums. We're going to see that again, or sorry, this is a sigma notation. We're going to see sigma notation cropping up when we do Riemann sums next.